saying is that if there's a 45th constant in nature, it's that I'll be late. So we're going to do a little bit of something that we kind of did the other day because I had a lot of fun. We had responded to, a video of PBS Spacetime. Today we're going to be viewing a very particular part of the DemystifySci Podcast featuring Dr. Alexander Unzicker. And we're going to provide a little bit of potential geometric insight at some recent work we did at the Physics Monastery. So, other than that, we're going to have a disclaimer, and we conjecture ahead.
Although this is going to be weird, and it's going to be about a different...
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Again, full disclosure, any potential hacking of universe is being done on a MacBook Pro. Just want to give as much disclosure as we realistically can. So we're going to pop in here. And this is the DemystifySci Podcast with Drs. Shoutout and Anastasia. And it's Dr. Unzicker, and we're just going to jump right into it.
Seems like solving these questions really comes down to having a really solid structure for the atom, including whatever it is that's connecting atoms to one another, which I would hypothesize is made out of the same stuff as the atoms themselves. And so solving those...
I mean, that sounds a little bit of Professor Wolfram's Atoms of Space, coincidentally named Eames. There's one thing I know about Eames, it's that they're pre-mimetic. Hey, Jax, what's going on, my friend?
Questions
We're reviewing a video.
Illuminate the answers to all of these other questions.
It says it there.
Yeah, we agree that it's an unsolved problem. And there is the best strategy is, allow any kind of ideas and everyone should be allowed to pursue very sick, crazily sounding ideas off the mainstream.
Totally agree.
Just allow that and then get back somehow to observations and link to that. And
see, what the good doctor is saying right there is very important. Hey, welcome, Whitechapel, my friend. But try to avoid eating the soap, Jack. If there's one thing I remember from Ren and Stimpy and Space Madness, it's not an ice cream bar. I'm just saying. Maybe in some quantum reality it is an ice cream bar. I don't think it's an ice cream bar. We continue here. But basically, observations are important because you can have the most beautiful theory in the world. You can have all the numbers, but if those numbers don't tell a story, it might be right, but I don't know. Is that the natural philosopher thing? Is that why I'm hearing all these things? Is this why Professor Carroll went to Johns Hopkins? I have no idea. But, we're going to continue. Absolutely. Rock on, brother.
My take would be on the light and matter question. That I like the constants discussion. And I think constants are important. And we need to explain them. And there is a relation of light and matter to constants. Light is obviously related to the speed of light. This is a constant. And matter is related to Planck's constant.
So for those of you that actually saw the thumbnail and the algorithm didn't automatically bring you here, I'm just saying, basically we had Planck's constant and the speed of light from NIST. Most recent, because they had done some updates back in 2019 or so. I think we're going to cover that in just about a second. But it's very interesting that those constants, they're made up of certain let's say dimensional flavors. Some may say speed of light. What's that? Planck length divided by Planck time. You get a bunch of orders of magnitude off? Yeah, it's going to be 300,000-ish meters per second. Okay, real quick joke. While we're at the monastery, I'm like, they changed it. It's like, when you I was telling that, I'm like, when you all of a sudden off the top of your head recited, the 10 digits for the speed of light, I'm like, whoa, this man has totally done a lot of things probably even without a calculator. He totally did a lot of calculations without a calculator. And then all of a sudden he just immediately responds. He's like, wait, there's only 9 digits. And I'm like, we are such nerds. It was a great time. Okay, but what he's touching upon there is the relationship in this. We're just going to finish off just for a few more seconds.
H, okay? And if you want to, this would be the corresponding two quantities to the concept of light and matter. Instead of explaining why light and matter, try to explain why nature needs this speed of light and why nature needs this quantum of action, which is an unsolved problem.
Okay.
These are again two.
Okay. Thank you. He goes into, I think he's saying like they're gods of nature or something like that. It's like I've heard Professor Michio Kaku talk about the God equation. I don't know about a God equation, but he said something like that would help it solve different things you could put on a t-shirt. Well, that's the wrong t-shirt. I put some stuff on a t-shirt. It's in some of the previous videos, but okay. Thank you, Dr. Unzicker. But links to the DemystifySci Podcast and Dr. Unzicker's Real Physics. They're in the link in the doobly-doo if anyone wants to check them out. So, now, where do we go? Oh, we're going to go somewhere different. Where am I going? We're going this one, code data. All right. According to code data, what do we got over here? All right. The fundamental physical constants. I clicked the wrong thing. We go back. Fundamental physical constants. Planck's constant. This is H. We call it H. The numerical value is 6.626 times 10 to the negative 34 joules per hertz. So -1. What the heck does that even mean? All right, we've got the... But now it's exact. I believe we actually used to have other digits. I think even in Thad's book, because what they did is they set a lot of these things to about 10-ish digits. I think a lot of these are 9 right here. Because it's like, all right, we want a coherent set of units using scientific, the SI system. And, okay, we're going to use scientific notation. We want it to be consistent. All right. So, and then we got the speed of light over here. Well, that's numerical values 299,792,000. Oh my God, how do I even say that? Oh, math is hard. 299,792,458 meters per second. Whew. That took effort. Okay, we got those numbers. That's cool. Why do I bring this up? Okay, meet the constants. H, the Planck constant. The Planck constant is one of the fundamental constants of quantum mechanics. It's basically like the quantum of action. It's basically the thing that happens. I think that's pretty neat. Quantum mechanics shows us that energy is exchanged and absorbed in specific amounts known as quanta. H defines the size of those quanta, which can be visualized as packets of energy exchanged by matter. In the revised SI, the Planck's constant H is equal to exactly 6.260715 times 10 to the negative 30 joule seconds. What the heck is a joule second? All right. This value for the Planck's constant was only finalized in 2017, and that value is key to redefining the kilogram. It's involved with a kilogram, Kelvin, and candela. What is that? Kilogram is essentially mass, Kelvin is essentially temperature, and candela is luminosity? Something like that. All right. So where do we go now? Oh, we're jumping ahead. That's the hyperbolic vortex equation. Link in the doobly-doo. All right. So Planck's constant. So we're going to go over to... No. I wanted to do this differently. All right. We're going to scare some people here. What is this monstrosity that Memes has brought up? Okay. This is to calculate essentially H. Or technically, this is H bar. You're going to see why in a second. What is this monstrosity we have here? As we know from our equations, we have our primary action and then our boundary actions. All right? And then whatever the terminal action is. See, for this right here, this is, oh God, what the heck did I do? There we go. All right. It makes more sense. Basically, for a lot of these, you'll have an action. The action for Planck's constant is actually 1. That's the primary action. Then we multiply by our boundaries, and then we have our terminal action. That's the construction to get basically most all the constants in nature. In the HF8, or that's minimal arena model. So what do we have here? So the dimensional flavors of Planck's constant are this right here, this Planck length, and that's squared. And that's the Planck mass, because it has to do with mass, right? Multiply it by the Planck mass, and that's all divided by the Planck time. Because if you've got stuff, it's going to do a thing. And that thing, what is that? That's a Planck second. It's 5.39 yada yada times 10 to the negative 44. It's really small. It ain't nothing, but it's really frickin' small. All right. What's the terminal action? That terminal action is composed of 1 plus, over here we have, oh, that's the wrong one. Oh my God, look how, that was one of the ones that I derived in my notebook. It was like gamma or something, but essentially you can rewrite it like this. Go ahead. No, that's just the boundary action. Here we go. All right. The benefits of live internet. All right. No, I went too far. All right. There we go. So our terminal action is this thing. I know I was passing off fake science. I apologize. Okay, so we got the same thing here. Planck length squared times the Planck mass divided by the Planck time. All right. 1 is our primary action. I mean, go figure for h bar, Planck's constant or reduced Planck's constant. We'll get into that. Then we multiply it by our terminal action. What the heck is this crazy thingy right here? This is 1 plus, oh, what's this? 1 over, that's the golden ratio squared. Oh, and this, what we're multiplying it by here, this is what we call J1 and J2, and those are squared. Those are from the hyperbolic vortex equation, the first and second answers here. Square the first answer, we get, at least according to Wolfram Alpha, and a lot of experiment supports it, and there are some experiments that say it might be off. Full disclosure. The fine structure constant. And this is actually the second fine structure constant, coincidentally. We don't need these right here. Those come in other places. But we go back over here. All right. So we got 1. That's times 1 over the golden ratio squared times the first plus the second hyperbolic vortex equation squared. Excuse me, hyperbolic J1 and J2. Those are our variables, or our answers for the hyperbolic vortex equation. I apologize. I should have had another cup of coffee. It's getting a little late. Still need to run. But, and then we multiply it by the inversion boundary. That would normally be 10 to the negative 7 here, so we go over. No. Zoom out. Go to the end. All right. See, times 10 to the negative 7 right there. But it's easier in notation to divide that all by 10 to the 7th. Essentially same thing. So this is our terminal action here. What's this number here? This is supposed to be h bar. Go back to the first thing. Planck's constant. Memes, you're off. You want to see some technomancy? I'm going to do some technomancy. All right. So in order to get the correct ingredients, in order to solve what I'm going to... there could be a better answer. We need more data. That's ultimately what it comes down to, and that's what Dr. Unzicker said. It's like you got to riff with reality. All right, I'm now gonna invoke 2 pi. I summon a circle. Go Wolfram Alpha. Oh, what's this number? Oh, look, more digits. Oh, we can have all the digits. Because this is a geometric answer. That's, I think, the benefit of doing this. All right, what do we get? We get 6.62. 6.62. 6070. 6070. 145. 1 5 and no more digits. Beams, you are off. You are correct. I am off from this. However, I think we used to know Planck's constant to a few more significant digits. We cut it off here and we're saying it's exact now. As far as I understand, we now assume everything past this is essentially a 0. Could be totally off on that, but what do we have here when we actually run that? Okay. The last digit's here. That was 1 5. This next digit is a 5. Call me naive. Call me naive. But didn't we learn like primary school that if it was a 5 or higher, we round up? And then like if it's a 4 or lower, we round down. Because like 5, you can go up to like 4 more. And like 4, you can go down 4 to 0. And then and the next digit's an 8. So technically, if we only have precision up to this last 9th digit here, if you had a 5 and 8, would you call it a 5? Now again, that's just full disclosure. We want to be honest. But what are we saying here? In order to get that, basically, we have a circular action multiplied by the space, mass, and time boundaries, or divided by time rather. You got an action. An articulation. You've got some stuff doing a very particular thing. Oh, and what's the last little boundary here? It's basically 1 times 1 over the golden ratio squared. That's one of those things that goes into basically... It's directly related to like the gamma function and everything. It's fantastic. People love it. It maybe not for all the reasons why people necessarily think. But it's really cool. Oh, times the first and second answers of the hyperbolic vortex equation squared times the inversion boundary. Okay. What was that other thing? Oh. That other thing, coincidentally, if we go here, because it's calculation, we go to Planck's constant. Let's go to the reduced Planck's constant. There's a reason why I'm showing you this. Because on Wolfram Alpha, you could still go out by what it was. Say, okay, we got these values. Because it's the 1, it doesn't have the pi in it. More digits. More digits. More digits. More digits. Okay, cool. The reason why I show this is, what do we got here? 1.05. 1.05. Wrong one. 457. 457. 181. 181. 764. Huh? 9. Oh, that's an 831 or something. Oh, no. It was 81. We want to get this accurate. 817. 816. Memes, you're off. Next digit's a 9, and how many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, look, the 10th digit. Didn't we just cut it off at 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. Totally a coincidence. So basically, you've got time, space, you've got space and mass doing a thing, being under the action of time. So basically something really crazy is happening in a really short amount of time. Okay. Oh, and it's directly tied over to essentially recursion within the golden ratio. Squared times the fine structure constant and the second fine structure constant squared times the inversion boundary. But okay, and again, I am just a dude on the internet. Hey, Demystify, welcome, my friend. Hey, awesome one. Oh my god, I've been rambling on for 20 minutes. I'm critically hitting people with all these numbers. I apologize. Okay, but basically, that was basically a quick derivation. We did the speed of light the other day. Quick refresher. Speed of light in vacuum C. Around 300,000. I'm not even sharing my screen. I'm such a terrible host. Around 300,000 meters per second. That's cool. Okay. What is this abomination? This abomination, again, the primary action for this speed of light, actually, that's probably a coincidence. The primary action is 1. So if we just multiply that by 1, we don't normally see the 1. That might be something interesting, because I think this is what Thad was saying when he told me, why do we call thing a prime like divided by itself and 1? Why would we use that terminology? We changed it in 1945 because I think it's some algebraic ring topology or something. I don't know. I'm not a historian. But, okay. I just ranted on for a minute about the history of prime numbers. It's like 20 seconds. But what's this? Oh, Planck length divided by Planck time. It gives us the speed of light to a bunch of significant digits. Now, here's where things get interesting. Oh, I just noticed something interesting. I learn so much every single day. But, okay. And again, primary action is 1. The boundary conditions of the Planck boundaries. Space and time. Cool. We multiply that by our terminal action, which is 1. And, oh, you guys are going to love this. This is the square root of the Giesecke constant. It's one of the 100 fundamentals constants of nature that we can know out to all the digits because they're geometric or whatever. We can keep on computing them. All right, that's cool. That also has the volume of the minimal non-compact 3 manifold. Don't that beat all? Here, we'll do this. So we'll go by hyperbolic figure 8 knot and resume our journey and stuff, because that's why I call it the HF8 model. That's a pretty thing. Oh, look at all the represent. I like that one. We've got some cool 3D ones, but it's a double cover. Double cover, they say, kind of like a Klein bottle. Well, it's basically already a Klein bottle. The Giesecke manifold. In mathematics, the Giesecke manifold is a cusp hyperbolic 3 manifold of finite volume. It's something that we can actually know. It is non-orientable and has the smallest volume among non-compact hyperbolic manifolds. It's got this beautiful equation here. It's got that blah, 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 those numbers. We won't get into the Clausian function. That's getting into the RB dragons. Yes, I know. But, all right. So we go back over here. So we got the square root of that. And that's times our first answer to the hyperbolic vortex equation here. Minus the second. All right. So it's getting a small number. Go back. And that's times the inversion boundary. That 10 to the negative 7. Just divide by. It gives us this number here. So, oh yeah, and the first one, again, maybe there's some better things. I just happen to think the golden ratio is a pretty beautiful answer, if it's true. This one, what's the speed of light? Speed of light in a vacuum. Its concise form is 299, 792, 458. 4, 5, 8. Oh, look, there's a 0 there. And then a 9. You could maybe round that out to 1. My friends, I mean, that looks like a geometric derivation of the speed of light. Could also say that looks like a geometric derivation of Planck's constant. Now again, I say this as somebody that's been following this stuff for a few years. Again, the only thing that really caught my attention, I'm like, Nolan happened to mention it. He tagged me after I was doing some light trolling of Professor Wolfram and Professor Keating. I'm like, these people know each other. Maybe they should know some of the different stuff and things that they're doing. I just think there's a lot of really smart people out there. A lot of us, I think we're all more or less working towards the same thing. It's like, what do we want to do? We want to see a better world. Why? Because we can. Or we could just destroy ourselves. I don't know. Are we Fermi's paradox? Social media not being able to get over ourselves? It's like, you're wrong, you're wrong. It's okay, you move on. But, see, for me, I'm like, all right, is all this model necessarily right? No, most of these are like on the second page of like Thad's chart and everything. It's like, do we necessarily have the highest confidence in those? No. The ones that we now, or at least Thad, I tend to agree with him, that moved up there are even. I'll let Thad release the video, and then we'll cover it, just because it's so freaking beautiful. One of the reasons is I noticed that Dr. Unzicker, he basically brought up h bar and the speed of light. These things are important. I'm like, that's cool. I happen to work on at least one of these. I've done Planck's constant and everything. Thad ended up finding most of it and everything. But it's like we're going through the process. He's showing me how. And at one point he's like, if something happens to me, at least another person knows how to do this. I'm like, I didn't know how to do it. It's like you sit down. It literally was like a monastery. It's like we're doing work, but instead of just shut up and calculate, it was calculate and conversate. Discuss what we're seeing. We were thinking about maybe streaming some, we're recording some for the first couple of days, but we were just having way too much fun. Just letting be, well, what if this happens? What if this happens? Oh no, we found something better. Oh, that's a cool answer. I mean, it was probably some of the most fun I had in a long time. I'm not sure if that's a good thing or a bad thing. I suppose it's relative. But, yes, memes of mathematics. I stopped understanding math like halfway through the 6th grade, and then, like, if there's a reason I was interested, then, like, it started to make sense. I don't know. Again, I feel like if you can make it inviting, give a person a reason and an interest, and make it fun, I think that's how we level up, or at least I'll claim. But that's all I got for now. Peace out, everybody. Thank you all for watching. Take care of yourselves. It's a wacky world out there, but I got some hope. Be safe, everyone.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.